Good evening, everybody. My name is Janice, and we're Team 1. This is Virginia, G, and Wayan.
So in this presentation, we are going to answer the questions that was proposed, and we are going to choose one material and choose one synthesis method to grow that material. And we are also going to show our teamwork. So the material we choose is barium 3 nail-bit 5 oxygen 15. It is one of the 5 candidates in the third group, which is the oxide and has a tetragonal structure. So the process that we used is to make a comprehensive comparison of all of the materials. And we found that the first one is only exists in literature and the zinc blend structure is not the ground state that was proposed in the Zoner's TRL paper. And so for the compressed silicon, at high pressure, the diamond structure is also not the ground state, and it also suffers from the problem of relaxation to its ambient properties when we use that for future applications. And for the third one, we found that it's also not the ground state. And for the others, they suffer from problems such as not stable or difficult to synthesize as thin film form. So consider all of these factors, which is barium 3 nail-bit 5 oxygen 15.
Our group had an interesting dynamic. We reached consensus on the material that had the best properties but could not be grown very quickly and got rid of it. That left us with the choice between compressed silicon and the oxides, and there was actually quite a substantial discussion there. Our theorists saw that the compressed silicon had the second best properties and the greatest potential for future improved properties. Synthesis for pure silicon crystals is well known. Silicon device integration is also well known. However, the characterization specialist noted that the good properties of compressed silicon would not survive outside of the diamond anvil cell, and that left device integration a problematic matter. Yet, it was still a very interesting material. It was our synthesis person who was able to provide the strongest case for the oxide group. When we looked at the oxide group, we were able to see that there would be flexibility in the choice of oxide, and device integration looked good. However, the synthesis was also going to be the strongest point and the weakest point at the same time, because the synthesis would be challenging. An interesting dynamic developed. It was our biochemist application specialist who really intensively listened to all the arguments pro and con, and then steered us in the direction of making a final decision. So the intensity of the listening and the final steering came from the fourth party.
So the growth method that we choose is molecular beam epitaxy. On the left is a schematic drawing of the technique, which is a chamber. So it mainly consists of some vacuum pumps and some sources. In this specific case, it will be oxygen, barium, and tantalum. And also it consists of a sample stage that is used for heating up and rotating the substrates. And in this case, we choose this substrate for the growth. And the reason that we choose this technique is because we think that it is feasible, it is worth trying, and also we can integrate our material with existing technologies.
So how did we encourage participation, equal amounts of participation for everyone in our group? As Virginia stated earlier, it's based on our strengths and our expertise in our science field. So Virginia was our characterization specialist. Boyan was our synthesis specialist, and we had, that was G. And Boyan was our theorist, and I was the biochemist key application person.
On characterization, first suggestion was to repeat the theoretical experiment. The results of the paper that we studied were for silver aluminum oxide, And we wanted to see that those would still be maintained in the barium niobium oxide. If that was the case, then these are very interesting properties. Oh, please.
Not requirements. Not.
All right. The very interesting properties include a wide optical band gap, an electronic structure that suggests that there is a 2-degree present, and what I put on the end there is a known 2-degree electronic band structure, graphene. If you can compare those last two, you can see the similarities in there. So the first thing to do would be to confirm experimentally the properties, if they hold up by theory, of good optical bandwidth. One could do that with UV vis. I would, I'm also familiar with photoluminescence. The electronic conductivity is the practical property we want. Hall effect is the tradition for that. I would also suggest an ID curve that is taken in a frequency-dependent manner to see if there are parallel paths in there. X-ray diffraction would be used for an elemental analysis. And again, the electronic structure could be assessed using the in situ ARPAs on the molecular beam epitaxy equipment that you have here. Finally, if you have a 2-degree in there, that 2-degree is created by a structure. It's a hexagonal material. Hexagonals can relax into various coherent interfaces. I would use HRTEM to go looking for those interfaces, and also some energy dispersive to get a finer rendition of what you get from the X-ray. Finally, a magnetic field applied to electrons passing in a 2-degree will give you an unmistakable signature of oscillations when you try to run a current through a high magnetic field as you increase the field. Those are Shulikov de Haas oscillations, and it would be a very strong confirmation that you really did have an interior quantum well that had developed.
So what unique information was shared in our group, and how did we use that information to solve our problem? Like we stated earlier, we wanted to use that diamond type silica, but we had our characterization specialist who had experience with that and said that it would be unstable outside of the ampicell, and then we had our theorist who was rooting towards that, and then we heavily relied on the information of our synthesis, our crystal grower, to lead us in the right direction, and that's how we solved that problem with that unique information given by our characterization specialist.
And Janice really pulled us together on that.
Okay, so in hindsight, what could we have done to get a better or more creative solution? So we think that better connection with teammates is very important, because we don't have enough time to meet with each other to talk about the problems we are assigned to. And we should concentrate more on the assigned question, not the tangential question or induced question, because during the way, for example, we are heading to A and we find something B interesting, although they're correlated, we should not concentrate too much on B. We should concentrate more on the assigned question A. So we make a detour somehow. And so we should, of course, work harder. If we had a solid theoretical foundation, we can get more understanding. And if we are proactive enough, we will be able to calculate the band structure by today, if that happens. Okay, and also it will be good if we had some other guys out of the group helping us to analyze some of the materials. Finally, if we could have a chance to see the real materials, we can get an intuitive understanding of the material. And for the theoretical part, how could the results generated be used for theories? So the theories, of course, will do theoretical analysis, and we can compare the experimental measures with the theoretical results. And in return, the theorist will help us narrow down the dictionary, finding the material ITC, as intrinsic transparent conductors. So for example, here these are the 3 band structures in the paper. And the first band structure is very good. The photons simply simply, the optical photon simply has no way to be absorbed. For the second type, it is promising, but we need to be careful that the phonon will play a role here for the indirect citation. In the case of the paper that compared the silicon, I already checked the full dispersion relations, and I finally find out that the phonon will play a significant role in the indirect excitation in room temperature, which will give us the compressed silicon is actually opaque at room temperature. But at low temperature, it will work. And for the third band structure, it will be ideal if we have P-type rather than N-type conductor, because the P-type, the holes can essentially go down, and there is a lower limit but no upper limit. So the P-type is preferred, and it could be transparent only in high light intensity. And that's the theoretical part. And here is our reference. And 6. Questions?
All right, so we're group number 2, and we're going to be talking about our selection for actually creating these intrinsic transparent conductive materials. So first I'm going to talk about the way we actually selected our material and the process. So first off, we obviously did a review of the crystal and the band structure of each of these materials, hoping that would suggest a clear winner in terms of the properties that we predicted. That really didn't help us out too much. So from there, we actually went about it in a slightly different way than a lot of the other groups did. We actually kind of did a reverse engineering based off of what material synthesis method we wanted to use. So we decided that we would use MBE. I won't get in too much because that's going to be his slide. But essentially, we wanted to look at which of these materials can actually be grown the way we want to grow them. So we started looking at things like the vapor pressure of these materials and what temperature they vaporized at. So immediately we realized that niobium and tantalum actually have extremely low vapor pressures, and it's almost impossible to form molecular beams out of these elements. So that immediately eliminated the 4 materials listed here. So then the next thing we did to hopefully down select some more materials is by looking at the thermodynamic stability. So we realized that silicon transforms into the beta tin structure above 11.2 gigapascals. So that was eliminated because we're trying to grow it at 50 gigapascals, which is already very difficult. Then we looked at this oxide with silver and aluminum, and we realized that that actually thermodynamically favors the phase including the another silver aluminum oxide phase, pure silver, and another corundum phase, and that would be partially insulating. So that immediately eliminated that material. So then we looked at RBTE and the zinc blende structure, and realized that that's also not thermodynamically stable, and it actually suggested that the rock salt structure is stable. So RBTE was eliminated. Wait a minute, that's all of the materials. So, so we went back and we took a closer look, and we found a reference, and it actually suggested that the rock salt structure of RBTE actually had arguably even more desirable properties than that in the zinc blende structure. So once we started looking more into that, we decided to go with it, and yeah, so.
That's my part?
Yes.
I actually have no idea. You? It's cliche.
This slide, what conflicts/disagreements arose and how did your group benefit from them? Some of the conflicts that we had was, of course, which material to choose. And the fact that we chose RBTE was that it was potentially had toxicity, problem with the toxicity levels. And the benefits that we gained from these conflicts, disagreements, we gained more information about materials. Well, we had to get more information about the materials before we made our final choice. And the ideas were presented as to how toxicity issue could be addressed.
So we choose MBE, and I'm actually biased in the oxide. But in terms of our discussions, RBTE is theoretically only existing. But if we use our reference, the rock salt structure is probably possible to grow, and the band structures looks like the same or even better actually. And so to create the zinc blend structure or rock structure, it's kind of layering sequence. So that is we can use the beauty of MBE, like that. One more layer, this is applied, and another layer. So this is the perfect for the MBE growth. And there's a skill challenge, as you may know. It's very volatile and very reactive. RB is very volatile, and we are not sure once we put it back into the chamber, we make some fire inside chamber. But they may figure out. And also the palladium, the TE is also very volatile. So we may need some specialized chamber if we need to decide to go using this material. Also the problem is we want to have a very lattice symmetric substrate to see the intrinsic property of the material. However, these materials suggest we need to find another substrate if we need to decide to grow these. Or another way, so we can use other substrate like voxel structures or like lithium fluoride or CSCl, but it may be very challenging to grow.
How did you encourage equitable participation of team members? So we did a homework on crystal and band structure. That was the decision-making point for us. The theory gave us a band structure for, with the zinc blade structure, the band gap was 3.28, and for the rock salt, it was 3.6. So that helped us to make a decision. And how discussion before final decision were made, we discuss about all the possible outcome of two different structures and which one is stable, which one is unstable, which one is more problematic, which one has an easy schematic to follow, and based on that we decided to look at both structure. So the characterization method. We decided to choose both, one without zinc blend, that is a rock salt structure, and other one with zinc blend. So we decided to see Hall effect to measure the carrier mobility and carrier density of the material, and read for in situ calibration during growth by MBE stoichiometry. And RPIS is the method of choice. Actually, we decided based on electronic band structure. And we also look at ellipsometry, that's the optical observation coefficient and optical band gap. And last two was UVVs. We want to see the transmitted and optical band gap of the material. And the standard method was X-ray diffraction, but X-ray diffraction is problematic for some cases, like the phase problem. So do we rely on X-ray diffraction if there is a phase problem? Even it gives us phase identification lattice constant, but in some cases there is a phase problem. So how to address that? Okay. Do you want to?
What unique information was shared in your group discussion, and how did you use this information to solve the problem? Half metallic spin polarized current. Knowledge of the stable rock structure opens the avenue for alternative substrate materials to control the crystal structure and properties. So we did discuss about the rock salt structure was actually better in the first slide. So that was part of the information that we used for the problem solving.
Okay, so looking back in ways that we possibly could have been a little bit more creative. So one of the things that really limited us was just the choice of only having 7 materials to really go with. So if we were given a little bit more material in terms of, what we could actually go with. I think we could have come up with a little bit more creative of a solution. We probably could have seriously considered other deposition techniques such as E-beam evaporation, which would have allowed us to use different elements. So going with MBE really kind of immediately, as you saw, narrowed down our selection to only 3 materials. And another thing that we considered is possibly modeling the strain response of other materials that could have possibly allowed us to rely on epitaxial strain to kind of tune the properties in a way that we wanted to. So we looked at the strain response in RBTE and saw that the properties that we were looking for were stable up to strains as large as 1% from DFT. So we thought that would be good. It would be pretty robust regardless of what structure we could grow it on, as long as we could maintain epitaxiality. But at the same time, we were largely limited by the lack of time and available literature. We would have loved to run these DFT simulations ourselves, but in a short time, we really just had to try and find it in the literature, and it wasn't available. So we went with RBTE because we found it was stable, at least in the rock salt structure. And also, the number of narcissists in our group, unfortunately, we had that lecture a little bit too late. So if we were going to go ahead and reform the group, we probably would have included the optimum number of 1.72 narcissists.
So last part is how could the results generated be useful for the theorists? So one of the applications that the author is eyeing over here is application to touchscreen sensors, solar cells, and various electronic devices. And we know that when you decrease the size of the devices, it keeps the heat, generates a lot of heat. And hence it's very important to look into the thermal properties of that materials. And it's known that this material is supposed to be highly electrical, should have high electrical conductivity, and electrons should be the major contributors of, should be major carriers of heat. But in a recent study, they used a DFT and DFPT and solved the Boltzmann transport equation and showed the contribution of phonons and electrons to the thermal transport in metals. And doing so, we can see how the various modes and the mean free paths contribute to the thermal conductivity of the material. So that could be predicted using DFT and DFPT. And so it's very important to, as I said, it's very important to look into the thermal properties. And so we can predict the thermal conductivity of the material and also look into the anisotropy, whether there is higher thermal conductivity in the in-plane or in the cross-plane direction. And also we know that there can be certain ways of tuning the thermal conductivity of the material, that is increasing it. So suppose if you strain the system, the bonds get stiffened and the speed of sound increases, and it's expected that the thermal conductivity increase. So running different simulations, we can also try to find what's the effect on the thermal transport of these materials and find if there is a way of increasing the heat dissipating capacity of this material. That's it.
Thank you. Did anyone have any questions?
Yeah.
So we're group number 3, and we decided on rubidium telluride. And we decided on this material basically because what we thought was feasible, what was the knowledge of everyone in our group. We also just looking at the 3 were attracted to the structure the most. We like the simplicity of the zinc blend, and we like how the band gap looked. And then we were thinking about, okay, what properties do we really want in transparent conductors? And just between the 3, this one looked like it was the most promising for that. We also used the process of elimination. We pretty much ruled out silicon pretty quickly because we thought it probably wasn't stable and would be hard to get, and even the properties didn't look that promising. And also, most people hadn't worked on oxides before, so they didn't really want to go into that too much. And also just that the structure is easiest, and it would be easier to do calculations on and then compare to the material. And what conflicts and disagreements arose, and did your group benefit from it? So we were all pretty unsure what we wanted to pick at the beginning. We were all really attracted to rubidium telluride, but we were also just unsure, and we're thinking maybe to go with one of the oxides, so we decided to just leave it for the night and think about it. We were planning on doing more research, but we were so busy that we didn't actually have time to. So when the next day came around, we just decided to go with our gut and go with the one that we all liked the most. So that's how we pretty much ended up with rubidium telluride.
So for the question is, what synthesis method did you choose and why? So for this material, once we decided the material, then we trying to do a little bit more search on this material, and we found that for this rubidium telluride, the phase diagram is shown in this diagram. Actually, the most commonly available is the RB2T. So that is, we can search many papers on that. However, for this RBTE, so 1-to-1 ratio, it's not easily. It's actually, there's a question mark. There's only one paper mentioned about this material. So exactly like the group 1 search, there's no, it's only existing in theory. There's no previous work on this. But we decided this is challenging, and if we manage to grow it, it'll be a big thing, right? So that's why we are going to use MOCVD method is because actually first we thought about several methods such as sputtering, evaporation, MBE, or MOCVD. And for sputtering and evaporation, we decided not to use it is because we are worried about it's not going to give us a crystal structure. It maybe end up with amorphous film, and it's not easy to find for example, for sputtering, it's not easy to find a proper target, and the source material, because rubidium is not a stable material. And for MBE, at first we thought MBE could be one of the methods, but we have an expert in our group who is doing MBE, but she actually suggested that maybe we need really a dedicated chamber to do that, and because of that, we may not be able to use that for anything else. So in the end, because of that, we choose the it's kind of rule out of all other methods. Then we choose MOCVD. It's the only feasible option because we remember that Paradim is going to build an MOCVD. That's one of very important reason. And also in literature, for the group of colchignite has been grown by MOCVD before. So that became a very strong reason for us to choose this method. And very importantly, we searched for the precursors for these two materials. For the telluride, we searched, we got something supplied, it's called telluride, yeah, something like that. Okay. For the rubidium, it's called rubidium aluminum double isoproposite. Yeah, it's all commercially available. So that's why in the end we decide on this method.
The other question was how do we encourage equitable participation of team members? First thing, we ask questions on each members. To if no participation, we just directly ask you the question too, so that we get to answer the question. We did a brainstorming together, just jotting our ideas about when we're picking the material. So we just asked everybody, what do you know about each material, and then that we did brainstorm on. Everyone was doing their own research when we did a overnight study to just go home and just think about it and just see how much you can read information from it. Everyone wanted to reach a conclusion before the end of the night. So that was the next day. So we already have another work that day. So we have to reach a conclusion. So everybody had to chip in order for us to proceed. No one knew a lot about the material. So yeah, everybody came from different aspects. So, but we knew everybody chip in something little from different directions. So that's what we added. And question is, what characterization methods do we choose? As we all know that this experiment has never been done just by theory. So we said the best structure that we can use is the XRD. We should actually give us the phase, so that would be like one of the best one. If we do grow it, so the SRD would be first we would do, and the TEM would be the second one. We should give it extra phase of the film to actually get the image if we should get any image out of it. the property that we expect, the property that we're going to expect to see is the band structure, the density of the states, the conductivity, and the absorbance and the reflection spectrum. And why do we choose this was because the reason word is like why we're choosing this way of method is, are we growing what we want? So the SRD and the TEM will give us that information. Does it have the property we're looking for, which is the band structure and the density, the conductivity and reflection? And we'd like to see a lot more characterization on this particular instrument, since it has never been done before. So.
So the next thing is the unique information we all shared. What happened is that all of us, we came from different backgrounds. So we have a theorist among us. We have those who know much about characterization. We have those who know something about material growth and things like that. So what we did was that anybody who knows something, so we share this information among ourselves, and that was able to help us to come to a conclusion. So what are the things that we'll have done differently? So if we have the time. So the first thing we did was that we jumped the gun. So without doing much research, we decided. So next time we'll first of all do a lot of research before we make decision. Then secondly, if we have enough time, so we'll be able to do something that is much more creative than this.
Okay, so as we all know, this material has not been grown now, but I think like if we try our methods after it grows, no matter it is the exact material or not, we can do the measurement mentioned above and compare with the theoretical simulations. Like since this material has a kind of simple structure and it's easier to simulate the XRD or TM or other like Raman data, and then we can compare with the experimental data to say if it is the structure we want. So that's pretty much what we have. Thank you.
Hey everyone, we're going to be presenting our choice of silver aluminum oxide. Now the challenge was to find, using the Zunger paper, a material that would be electrically conductive and transparent. So before we even selected our material, we thought about going more of a device-oriented selection method. So what would be most attractive to a company like Intel or whatever device manufacturer? So we picked, so immediately our thoughts were we want to eliminate any material that has rare earth metals or is very expensive. And then we also thought about our areas of expertise, which Jess will get more into. But for example, my research is involved in making devices out of graphene and HBN. So I had that perspective, and that's kind of what pushed me toward pushing for silver aluminum oxide, because it has this hexagonal structure, and graphene and HBN are also hexagonal. So I knew a little bit about how you can make heterostructures out of that. And then we each had our own contributions of how we end up with this material. But one of the other exciting things about this material is that it has that 2D electron gas. So again, the parallels with graphene and how that's an exciting area of electronics.
Wait, who's this one? I don't remember. This is you. I guess so.
Okay. So in order to get to our final choice, we actually have a discussion, and because again we come from different backgrounds, so we trying to talk about the advantages and disadvantages of each material in the papers, and then we narrow down to two material, which is the silicon and these oxides. And then when we consider how accessible the material into synthesis and also for devices, and we finally came down to the final choice with the silver aluminum oxide. Yeah. Okay. And from discussion, we actually learned a little bit more about different areas that we're not the expertise on. For example, I'm doing bulk crystals, and I had no clue about layer materials or thin films techniques. So this is really a good advantages for us to learn from each other.
So we actually took a different route for our synthesis method, not something that Paradim will have, but we were thinking of doing pulsed laser deposition, or as Ramesh at Berkeley calls his system, a laser MBE. So the reason that we were drawn towards this, as Dip mentioned, we were thinking long run we wanted something that could transfer to industry easily. As much as I love MBE, it's not as common in industry versus PLDs much more. And it says in the paper that it's 7 milli-electron volts per atom above its stable, so that is close enough that we viewed that as we can make that stable, probably. That's a pretty low number. So how pulse laser deposition works is you basically make a pellet out of your target material. So like you could straight up like mortar and pestle it and to grind it all together and make a puck, and then you put it in there and then you shoot it with the laser, so then it comes out over here. Unfortunately, the person that knew the most about PLD is not here right now. So that's what the method we went with, and then the other idea of why we wanted to use a thin film approach is because you can use different substrates if you can get an epitaxial relationship and strain it a little bit, which can affect structures down the line. So that is why we chose PLD.
To encourage the participation, at the first day, we asked about our area of expertise and our knowledge. And for each question, all the members, we participate with maybe opinions, experience, like Jessica, and maybe some extra information that we have.
So then, once we make this, the primary ways that we thought to characterize it is we want to start with X-ray diffraction. It's a good way to confirm your composition and to verify the lattice constants. Since we want this to be a transparent conductor, the next two things are to make sure it can conduct. So we could do resistivity measurements as a function of temperature, because often that changes, and to figure out what regions in which this would be best. Use a Hall measurement in order to determine not just the type of carrier. This isn't in type, so we should know that already. But and then to get that carrier density, which is a nice factor for later. And then we want to use what Sandra taught us about of spectrophotometry, which can actually just give you the transmittance as a function of wavelength. So then that would be a good way for us to determine the range over which it is indeed transparent. And then ARPES is a wonderful way to confirm the band structure. So that is something that we could also do here at Paradim. And since there are simulations of it in the paper, we could experimentally determine and compare them.
So like we mentioned earlier on, that we come from different backgrounds, so we share unique informations. So for example, some people have expertise on thin film, so we learn the techniques for synthesis, and also we have people from characterizations. And actually, I really acknowledge the fact that we have different background. That way we can learn and we can share the information. And the way we work together is that we always respect each other's opinions, and we try to learn from each other. So that's how we do it.
So in hindsight, what could you have done differently to come up with a more creative solution? One of the big things for us was we wish we had the opportunity to do a more thorough literature search. Most of our decisions were just based on our personal experience and research experience, but to have been able to go through and consider like all the possible materials and really take the time to understand everything at a more fundamental level would have given us more confidence in our choice. And we also didn't do a full synthesis search. Mohammed, our missing team member, was the one who told us about this other synthesis technique and kind of just trusted that that was the best possibility. But obviously there's more than that and so we would like to look around more. And how could our results be used by theorists? So in the paper they talk about a bunch of different pieces of information that theorists use to decide what they think would be insulating and conductive. And so they had guesses for what the lattice parameters were, and that's why we wanted to do XRD. We wanted to do ARPIS for the band structure information. And one of the things that the paper said was they thought a low plasma frequency corresponded with being transparent. So that's why we wanted to do the Hall measurement combined with ARPIS, because the Hall measurement would give us the electron density, and ARPIS would give us the electron effective mass. So using those two, you can calculate plasma frequency and kind of see that the value they calculated is that actually what it is. And if it's not, what corrections need to be made.
That's it.
I'm Michael Quintero, and they didn't want to introduce themselves. So they might do that later, but let's get started. The first question that we had was, what material did you choose and what process did you choose to select it? So we chose silver aluminum oxide, and there were a few reasons, and in no particular order here. We have some of the larger ones. One of them was cost. A lot of these materials there's no promise that you can make them necessarily. They're hard to make. If they weren't difficult, someone else would have done it by now. We wouldn't be reading a very interesting theory paper on them. And we wanted to pick something that we could potentially try multiple times. Some of these starting materials could be quite expensive. Another deciding factor was previous work, and by that we mean some of these compounds are not reported as being synthesized yet. And we really wanted to sort of limit how much work we had to do in terms of finding something that we could study. So we wanted to pick something that had a reported synthetic method, which we were able to find. And the last one was the physical properties of some of our starting materials. One of the compounds listed in the paper contained tantalum. Tantalum is something that is extremely hard to melt and hard to work with from just about every synthetic perspective I can think of. Most people try to avoid it, and we followed suit. And there were others, but this sort of paints the picture of why we settled on this compound. Let's see, that work? Now, as for conflicts and disagreements, we really got along, so we didn't have too much interpersonal conflict. But one of the, I guess, conflicts with respect to the problem we were tasked with was deciding on ideas that were ideal and practical. In a perfect world, you want to make the best possible material and do all the tests. You can't really do that. If you want to grow a single crystal, well, that's going to make it more difficult to do something like ARPES. If you want to grow a thin film, well, now you're going to have to sort of pull back. One of the examples was the compound we selected is predicted to have a two-dimensional electron gas, and one of the ways to measure this would have been to measure the in-plane and out-of-plane conductivity. That means you have to decide whether or not you want to do a single crystal or film, because you can't necessarily decide how that's going to grow. As for which way we ended up choosing, someone else will say. But this sort of highlights the kind of decisions and conflicts that we were dealing with. And it's sort of problems like this that led us to really question and evaluate what we initially thought, what our original plans were, and forced us to really optimize what we wanted to do. We wanted, as all scientists do, to pick the material and the synthetic method that would sort of give you the biggest bang for your buck. And it's sort of these types of conflicts that really forced us to think critically about why it is that we wanted to do what we wanted to do and whether or not it was the best decision or not. Yep, that's next. Go.
Okay, so we also decided to grow the material by MBE, mainly because it is slightly metastable, and so we figured this might be a good way to get at a non-ground state phase. And also, MBE is well known for giving single crystal material or just very high quality material. And when you're comparing to theory, it's a lot easier to compare to theory's perfect world if you have a single crystal. So we felt like that would make just the determining whether or not we're getting the phase right a little bit of an easier thing to get at. And then also what we liked about it is that there's two things. We've got this in situ read that's pretty common on MBEs, so we could get at the structure while we're growing. And then there's ARPAs on the MBE system integrated in the vacuum system here. And so that seemed like a really great opportunity to compare the band structure that we got experimentally to the band structure that was predicted in this paper. So we encouraged equitable participation by making sure that each member had a chance to speak. We wouldn't make a decision before hearing from each person in the group. And then we made sure to divide the slides equally for presentation and preparation. And then in that division, we made sure that each person had a technical slide and like a group dynamic slide.
Okay, for the first question in this slide, what characterization method did we choose? We chose total 6 characterization method. In order to characterize whether or not we grew the correct material or not, so we chose width, TM, yields. So width can tell us basically the material information only on the surface, so that we can characterize the materials while we are growing the material. And then TM will tell us as you see the pamphlet of the paradigm, we will see the exact atomic or electron density of the mapping. And then the iris can tell, which is attached normally the TM, can tell us the chemical composition of inside the material. So of course, and then for the property characterization, we chose RPS and full probe conductivity measurement and UV visible spectroscopy. And how and why did we choose this characterization? For the synthesis characterization, there are a lot of discussions and debate. But yeah, of course, the more characterization tool we use, the better we will understand the material. But it's kind of waste of time and money. So so the crystallographic information plus chemical composition will tell us that these three tools will be enough for the to confirm that we grew correct material or not. And for the property characterization, it was kind of obvious. So we first have to confirm the electronic band structure is corresponding to the theory, and then we have to characterize. We have to confirm that whether it's conducting or not and transparent or not. And what unique information was shared in our group in discussion, and how did we use this information to solve the problem? So whenever we faced the problem or come up with some concern, basically we solved that kind of things by sharing each member's background and experience, and these are some examples. So someone who has an experience of the full probe measurement, she concerned about the material that we are growing is going to be too thin and might be damaged by the contacting the probe. So someone who has experience of the bulk material had come up with the solution. We can use a metal paste or metal paste for this problem. And another thing is, someone is really curious about how we can prepare the samples for the TM characterization, and someone brought the solution is gonna be focused ion beam. Or the last thing is, for the ambiguous, the substrate is really important. And then we associate, the crystallographic information. And then the sapphire has a hexagonal unicell, which is exactly the same to the crystal structure of the, which is same to the unicell of the material that we were going to grow. And then the chemical ratio between the aluminum and oxygen is similar to that range. So yeah, that's what we concluded how this material substrate chose.
So in hindsight, what could we have done to come up with a more creative solution? We could have been a little more risky in our choices of materials and synthesis. We actually chose our material fairly quickly, and we went through that based on, is it feasible, is it cost effective? So we could have been a little more risky in our choice of materials and synthesis. We could have been a little more thorough in sharing the information, the different information that was coming from different members of the group. We just kind of brought up things as they came along. We could have kind of tried to really evaluate at the beginning what sort of strengths each person was bringing to the team. And then finally, as another group previously mentioned, we did only have one narcissist in our group, and optimally we would have improved our creativity with 2 narcissists. And finally, how could our results be the results we generate be used by theorists? They could be, because we had chosen characterization methods which specifically matched the theoretical properties that had been calculated, and we chose high quality experimental methods to do that, then we'd be able to compare to the theory and help them evaluate their methods, see how accurate the theoretical methods they used were, and then hopefully refine those methods so that whatever they use can be more closely matched to the experiment and then can be further used to evaluate other materials which haven't been made yet and be producing accurate theoretical properties. And we would help people like Alex Singer realize his dreams. And that is all we have.
How does the teamwork solve the challenging problems? That's why I be here for the week-long Paradim summer school courses. Definitely, our team members are from different research fields, from chemistry, physics, and material science. How do we communicate to share the knowledge, experience, and creative idea to work on preparing 8 slides?
Okay. So the material we chose is the strontium niobium oxide, and the reason we chose this one over the others is because we actually took 2 days to pick this compound, 2 nights. And in the end, we reached to this one by process of elimination mostly. The rubidium telluride we didn't like on the simple basis that Rb2Te would probably be the stable phase there, given rubidium 1 plus and tellurium 2 minus. The silicon, as already just been discussed by others, does not exist in the diamond structure at 50 gigapascals. And then the others were all fairly similar. So the barium niobium oxide, the barium tantalum oxide, those could all be made. I'm not very sure. I don't really know how MBE works, but they could all probably easily be made as single crystals through flux growths or through floating zone techniques. And so we picked this one in the end, not necessarily because, I mean, it wasn't discussed in the paper. It was only referenced as something that could be interesting. And the reason why this one seemed also interesting, besides the fact that it could also potentially be a transparent conductor, is the fact that it was proposed to be non-centrosymmetric, and polar as well, which could lead to multi-ferroic properties, and could also lead to the fact that you could have a non-linear optic system going on. So it was, in general, a interesting system, besides the fact that it could also be a transparent conductor. So it had lots of properties that we could all probably want. Toxic, it's not toxic at all. Niobium oxide is not as toxic as anything else you might find. And it's abundant. It's it's not expensive either. None of these materials are expensive, and so we could probably grow this material easily.
Yeah, so, oh wait,
Right.
this is yours.
Is it? Okay. Is it? That's it. So conflict, there really wasn't that much conflict. We had conflict. We had some conflict deciding who was going to say what, but besides that, we all pretty much cooperated. None of us are children. We came to this conclusion together. We all liked. I don't know. We all interacted nicely. Had our jokes, our fun, our giggles. But the interesting part was the very varied background, right? Thermoelectrics, right? Chemistry, and so. MBE, yes, MBE characterization, floating zone, single crystal, chemistry, basically chemistry, physics, material science all came together to decide on these compounds, and so we all contributed. And yeah, so there was little to no conflict. That is the take home.
Yeah, so we decided that MB could be a possible way of synthesizing this, but we thought we could also make it using single crystal methods as well, which we're going to talk about some more. We would probably grow it using an E-beam for niobium because high melting point. And we would like to choose a transparent substrate. Yep. So the nice thing about combining single crystals and MBE is that we can use a method that's like pretty fast and produces high quality materials, so single crystal, but then we can also use tuning parameters available in MBE, like changing the strain state. And another thing we could do is actually talk to the theorists while we're growing the material, so ask them what substrate to use, rather than waste a lot of time growing materials on substrates that would maybe push it into a state that wouldn't be transparent, for example.
All right, since apparently everyone seems to know what MBE is here, how many of you have actually worked with a floating zone before yourselves or seen one? Okay, just compared to MBE, just for curiosity, how many of you have worked with MBE? All right. Okay. So the floating zone technique is a technique that's used to grow single crystals. And this particular crystal, this particular material would benefit greatly from this. And basically, the idea is that we would have to pre-make the sample via an arc melter or just solid-state reaction in reducing conditions, because we do have niobium in reduced oxidation states, which probably leads to its conductivity later. And the idea is that we take a rod of the pre-made material and we put it in contact with a comparable crystal, material that is of a comparable structure that is already a crystal, or we just hope for spontaneous nucleation, and we blast it with incredible heat. We blast it up to 1,700, 1,800. There really is no measure of temperature on this, more than we can measure the power output of the lamp. And so this focuses all of the heat onto a single point on a rod that is then lowered slowly, and that makes the sample at that point melt. And as it comes out of that point, it immediately crystallizes, it immediately crashes out, and so you get a very long single crystalline rod. And so we could definitely do it for this material. In fact, I think it was done for this material, using niobium oxide as the solvent, which melts at 1,500, which to us is a lot, to the floating zone is nothing. And so a single crystal could definitely be used, if cleaved correctly, could also be used for some of the characterization techniques we're going to discuss later, but MBE thin films are ideal for that.
Right, so how did we encourage equitable participation of team members? Well, first we all went around and discussed our various backgrounds and talked about what we could contribute to this process and how even if we didn't have a lot of background knowledge in the specifics we were doing, we could still help with bouncing ideas off of one another and coming up with a solution to this problem. We made sure to listen to everyone's input when they talked, and we went around and made sure we all agreed on what we were doing, and everyone was given a chance to speak during this process.
For characterization, we will primarily use ARPAs and XPS, so in situ measurements. ARPAs will, as everyone has talked about before, give us band structure. So even if the material is not what the theorist predicts, we can give a feedback to tune their models.
And XPS would be useful, especially I think for the single crystals, to get an idea of the stoichiometry. Yeah, and then we can also do transport, and because we want to grow this on a transparent substrate, we'll probably do some visible spectroscopy.
Cool. So what unique information was shared in our group discussion? How did we use it? Well, as I mentioned, we all contributed information about our specific backgrounds in synthesis, characterization, and theory. And in addition, we all did individual literature searches and contributed what we learned during those lit searches for the past week. And this led to a lot of ongoing thoughts about our process and what different backup ideas we would have, and we all contributed to this resulting synthesis method.
Okay, in hindsight, what we could have done differently to come up with a more creative solution. We wrote a couple of points that we talked about, like we could talk to theorists who wrote the paper to have a better understanding what they did and try to see whether whatever they have done is really accurate. We can also seek another opinion to see what they have done, people who have similar expertise in theory. We could conduct our own DFT calculation. Some of the calculation is not too hard, as we have seen over this past week. We can do a more thorough literature search, like because we need to come out with these slides like in 1 week, so we sort of do like a half-baked job, I guess. And for MBE, calculate the effect of strain. Okay, yeah, sure. So I guess in order to use MBE, we have to have lattice matching. So we could have actually calculate the strain that could have induced when we use a slightly mismatched substrate to deposit our material. Another point that we thought of, I guess, is off the cuff, is that we should have taken a step backward to see where this project is actually leading us to, in a sense that is this just a confirmation of what the paper has wrote, or is it something that's leading to a device that we should build, or is it something to create a new material? What's the impact? And then from there, maybe we could come up with more creative solution, whether we should follow whatever the paper has written, or looking at the grand theme of this project. So the last slide I have before everybody can go off is how could the result generated be used by theorists? Everybody, all the rest of the team, we have said that we can use to verify or discount their prediction, compare experimental band structure to what is predicted, and also confirm and deny their approach. We can also use this to actually to discuss with theory, we found this experiment result, okay, this is what you have predicted, this doesn't match, so what's happening? But one thing about theory is this, most of the most accurate methods, which is like DFT, actually takes up a lot of computational time. It's very accurate, but takes up a lot of computational time. So what we could have done is we could have looked at our experimental data, and then we could see a way to cross-grain the theory or the results of the DFT, in a sense, moving from DFT to something more coarse, but giving us almost similar accuracy, like molecular dynamics. The reason being is also DFT is their result is mostly calculated on using a temperature of 0 K. So whatever experiments that we have done might not be directly correlated, or the results could correlate directly to their structures. So using MD, which we can actually perform at higher temperature, we could actually do a much better job. But of course, sacrificing some accuracy, but at the same time, we could simulate a much bigger system, then we might be able to get a better agreement. Yeah, and also at the end of the day, with the results, some of the more traditional theories, those who use pen and paper to write out some grand equation, could actually do that, in the sense that we could actually have one equation to actually predict some of the properties that instead of doing calculation, which takes quite a lot of time. Yep, that's it. Sorry.